Okay, so today's lesson is looking at the shortest path when we're referring to networks. So just to recap, networks can be directed or undirected. A weighted graph is a graph that has edges that have a value associated with them. Now we call these weights. That's why we call it a weighted graph. So the weight of an edge usually represents the cost or the distance between two vertices. So in our picture here, the cost or the weight of that edge indicated there is 3. The minimum spanning tree is the spanning tree that connects all the vertices together and has the total edge weight. However, the minimum spanning tree does not always provide the shortest path between 2 points. So if we considered this network here, the minimum spanning tree for this network would be 4, 8, and 5. However, the shortest path from A to C would be 9. Otherwise, our path would be 17. So 9 is a bit shorter than 17. So unlike the minimum spanning trees, shortest paths do not need to include all the vertices within a network. So if we want to find the shortest path between two vertices, it becomes much trickier when we have to take into account the weights of the edges that we are traversing through. So what is the shortest path from A to B? So taking the route direct from A to B is 5. So that will cost us 5. However, if we were to take the route ACB, that cost will only be 3. So our shortest path will be ACB. When we are looking at the shortest path, we can use Dijkstra's method. So how this method works is we move to our starting vertex. Then we label all directly connected vertices with a tentative distance. So that's how far we've travelled to get from our first point to the next point. Then we move to the vertex with the smallest value and relabel all the directly connected vertices with, if smaller, a tentative distance. Then we move to the next smallest vertex and repeat those steps again, and we repeat until all of our vertices are covered or the goal vertex is reached. So if we consider this network here, we want to find the length of the shortest path from A to B in this network. So we're going to start at A and we're going to put our tentative distance in for all of our vertices from A. So that will be both 10 and 10. Now we're going to move to our next vertice. So we could have moved to the top vertice or the bottom vertice. It doesn't matter which one we choose because both of them are 10 and it won't change the result in the end. So from here, we're then going to look at all of the vertices that are coming off that we haven't already covered. So we're going to get 14, so 10 plus 4 is 14, 10 plus 2 is 12. So we're going to put in those tentative distances. Now our next shortest path so far is the 10 up the top there. So we're going to go to that 10 and we're going to look at the edges that come off that vertice. So our first one's 10 plus 7 is 17, 10 plus 5 is 15. So we're not going to do anything with that vertex because our tentative distance of 14 is still shorter than our tentative distance of 15. So then we move to our next one, which is our 12 down here. Now we look at our things, the vertices that come off that. We have our 3 and our 8. So 12 plus 8 gives us 20. 12 plus 3 is 15, so we ignore that. 20 is not our shortest distance on our graph. We want to keep going until 20 is the shortest distance. So we look at our next one, which is our 14. So from 14, the only direction we haven't gone is towards the 17. 14 plus 5 gives us 19, which is going to be longer, so we don't need to go any further with our 14 there. Our next shortest is our 17. 17 plus 4 gives us 21. So we've covered all of the vertices in our graph going across, and we have the shortest distance here of 20. So our shortest path from A to B would be A plus 10 plus 2 plus 8, which would give us a result in 20. So that would be the shortest path on our network.